Hello, welcome to another exciting class in physics. I am Wuzo Gift. Our topic today is Simple Harmonic Motion, Part 1. Imagine a world where everything is stationary. You neither move nor things around you. That would definitely be a boring world indeed. But the good news is that we move and objects around us move as well. The way and manner these objects move differ. Let's go on to see our lesson objective as we proceed. By the end of today's lesson, you should be able to define simple harmonic motion, and you should also be able to show the relationship between period and frequency. Motion is a term that is used to describe the movement of objects. In physics, there are basically 4 types of motion. We have the rectilinear motion, circular motion, rotational motion, and periodic motion. For this class, our focus will be on periodic motion. Periodic motion is simply a type of motion which describes the repetitive movement of objects over a given period of time or regular time interval. Examples of periodic motion include the motion of the Earth around the Sun, the motion of the hands of a clock, and so on. But don't forget, our topic for today is simple harmonic motion. What then is simple harmonic motion? Simple harmonic motion is a special type of periodic motion which describes the to and fro movement of objects away from their equilibrium position or fixed position on a straight line. In a simple harmonic motion, the force which tries to pull the object back to its equilibrium position is called restoring force, and it is usually proportional to the magnitude of the displacement but opposite in direction. Now going on, some examples of simple harmonic motion are the motion of a guitar string. When you strike a guitar string, it continuously vibrates upward and downward until it finally comes to rest. Such upward and downward movement describes simple harmonic motion. Another example of simple harmonic motion is the motion of a body suspended by a spiral spring. Next is the motion of the pendulum of a clock. And lastly, we have the motion of a swing. For a motion to be called simple harmonic motion, there are certain conditions that must be met. Let's go on to see them. The first condition is that the acceleration as well as the restoring force must be directly proportional in magnitude to the displacement of the body from its equilibrium position. Now let's consider the motion of a simple pendulum. A simple pendulum consists of a body of mass called bulb hanging on one end of a string that is fixed on the other end to a rigid support. At this point, the bulb is said to be at its equilibrium point or fixed position. Let's call it point O. If this bulb is displaced to a point on the right, say point A, and released, it forcefully moves through the equilibrium point to a point on the left called, let's call it point B. And from point B, it moves again through the equilibrium point to point A. And this cycle continues until it finally comes to rest at point O. The force which tends to move this bulb from either point A or B towards its equilibrium position is called the restoring force, and it is directly proportional to the magnitude of the displacement. That is, the further the displacement of the bulb from the equilibrium point O, the greater the restoring force that pulls it back to the equilibrium point. The next condition that must be satisfied for a motion to be termed simple harmonic is that the direction of the restoring force as well as the acceleration must be towards the equilibrium position. Let's consider our example of simple pendulum. Notice that the restoring force always pulls the bulb from point A or point B towards the equilibrium point O. So a simple pendulum can be considered a simple harmonic motion. To represent those two conditions mathematically, we have A is directly proportional to minus S, which implies A is equal to minus Ks, where K is the constant of proportionality, S is the displacement from equilibrium, and A is the acceleration. Also, F is directly proportional to minus X, which implies F is equal to minus Ks, where F is the restoring force, K is the constant, and X is the displacement from equilibrium position. Now, it's important for you to know that the negative sign shows that the direction of the restoring force or acceleration is towards the equilibrium position. Having known the condition that must be satisfied for a motion to be called simple harmonic motion, let's go on to define some terms associated with simple harmonic motion. First, we have the cycle. A cycle is completed when a body undergoing simple harmonic motion moves to and fro. It is denoted by the symbol N. A cycle is also called oscillation or revolution. Next is period. Period is the time taken for a body undergoing simple harmonic motion to complete one cycle. It is denoted by capital letter T and measured in seconds. Mathematically, period capital letter T is equal to small letter t over n, where n is the number of cycles and small letter t is the time taken to complete the n number of cycles. Next, we have frequency. Frequency is the number of cycles a body performing simple harmonic motion completes in 1 second. It is measured in hertz and denoted by the symbol F. Mathematically, frequency F is equal to n over t, where n is the number of cycles and t is the time taken to complete the n number of cycles. If we consider the mathematical representation of frequency and that of period, we will find out that frequency is the inverse of period t. Therefore, frequency can be written as F equal to 1 over t. The next is amplitude. The maximum displacement of a body performing simple harmonic motion from its equilibrium position is called amplitude, and it is denoted by the symbol capital letter A. Going on, we have restoring force. Restoring force is the force which tends to move a body undergoing simple harmonic motion back to its equilibrium position. Next, we have angular velocity or angular speed. Angular velocity is also called angular frequency. It describes the rate at which angular displacement changes with time. It is denoted by the symbol omega and measured in radians per second. The magnitude of angular velocity is called angular speed, and mathematically it is represented as omega equal to theta over t, where theta is the angular displacement and t represents the time. It is very important for you to know that angular velocity, angular speed, and angular frequency are used interchangeably. Going on, we have angular acceleration. Angular acceleration refers to the rate at which angular velocity changes with time. It is denoted by the symbol alpha and measured in radians per second square. Mathematically, alpha is equal to omega over t. Next, we have linear velocity. This is the rate at which linear displacement changes with time. It is denoted by the symbol v and measured in meters per second. Lastly, we have linear acceleration. This is the rate at which linear displacement changes with time. It is measured in meters per second square and denoted by the symbol a. Having described the terms associated with simple harmonic motion, let's go on to show the relationship between period, frequency, and angular velocity, which are some of the terms that have just been explained. Recall from our definition that frequency f is the inverse of period t. Therefore, f is equal to 1 over capital letter T. Making period t the subject, we have t is equal to 1 over f. So period and frequency are the inverse of themselves. Also, we define angular speed as omega equal to theta over t, where theta is the angular displacement. Please, let's take note of this expression. We'll be needing it later as we proceed. Recall from our definition that a cycle is the number of oscillation or revolution. When a cycle is completed, the angular displacement theta is equal to 360 degrees or 2 pi radians. Recall that our omega is equal to theta over t. When the total number of cycles completed is equal to 1, that is n equal to 1, the period capital letter T is equal to the small t, since t over 1 is equal to t. And the angular displacement at such point is theta equal to 2 pi radians. Now, substituting period capital letter T for small letter t and 2 pi for theta into this equation, we have omega is equal to 2 pi over capital letter T. This gives us an expression that relates angular velocity with our period capital letter T. When we make period the subject of the relation, we have t is equal to 2 pi over omega. But recall that frequency f is equal to 1 over t, that is the inverse of period. When we substitute 2 pi over omega for period here, we have f is equal to 1 over 2 pi over omega. And by simplification, f is equal to omega over 2 pi. That is, f is equal to 1 times omega over 2 pi, which gives us f equal to omega over 2 pi. This is the expression that relates frequency with angular velocity. When we make angular velocity the subject, we have omega is equal to 2 pi f. Having shown these relationships, now let's go on to solve some examples. Example 1. If a vibrating body makes 50 cycles in 15 minutes, find its A, frequency, B, period, and C, angular speed. Now, before solving calculations in physics, it's important for you to take note of the values that are given in the question, the parameters you are solving for, and the expression that relates the parameters you are solving for with the values that are given in the equation. Now, let's proceed. From our question, we are given that the body makes 50 cycles in 15 minutes. That means our n, the number of cycles, is 50 cycles, and the time taken to complete the 50 cycles is t equal to 15 minutes. Having known the values that we are given in the question, the first thing we are to solve for is frequency. And frequency is cycles per second, given by the formula f equal to n over t. This is the expression that relates frequency with n and t. But our t is given in minutes. We have to convert it to seconds before solving. 60 seconds make 1 minute. Therefore, our frequency f is equal to 50 over 15 times 60. Here we have 15 times 60 because we are converting 15 minutes to seconds. Solving through, we have 50 over 900. 15 times 60 is equal to 900. 50 divided by 900 gives us 0.055 Hz. The next parameter we'll be solving for is period. And remember that period is the inverse of frequency. That is, t is equal to 1 over f. Substituting 0.055 for frequency in this equation, we have t is equal to 1 over 0.055. This gives us 18.18 seconds, which is approximately 18 seconds. The final parameter we are to solve for is angular speed. The expression that relates angular velocity omega with frequency is omega equal to 2 pi f. When we substitute 0.055 for frequency in this expression, we have omega is equal to 2 times pi times 0.055. This gives us 0.11 pi radians per second. Example 2. If it takes a body 5 seconds to complete a cycle, calculate its A, angular frequency, B, frequency. Solution. From the question, we are given period t as 5 seconds. This is because from the question, the time taken to complete one cycle, that is the period, is equal to 5 seconds. We are to solve for angular frequency and then frequency. The expression that relates angular frequency with period t is omega equal to 2 pi over t. When we substitute 5 for period capital letter T, we have omega equals 2 pi over 5. And this gives us 0.4 pi radians per second. The next parameter we have to solve for is frequency. Remember that frequency f is the inverse of period t. Therefore, substituting 5 for period t, we have f is equal to 1 over 5. This gives us 0.2 Hz. Don't forget, Hz is the unit for measuring frequency. Having solved those examples, we'll finally come to the end of this class. But before we go, let's take a quick summary of all we've learned so far. First, we've learned that a motion can be called simple harmonic motion if the restoring force is proportional but opposite in direction as the displacement. Next, we defined some terms associated with simple harmonic motion, such as period, frequency, angular speed, restoring force, amplitude. Going on, we saw that angular speed is also called angular frequency. And lastly, we learned that angular frequency can be related to frequency by the formula omega equals 2 pi f. It's question time. Our first question is, which of the following is not true of simple harmonic motion? A. The acceleration acts in the direction of the fixed point. B. The restoring force is equal in magnitude to the displacement. C. The restoring force acts in the direction of the displacement. D. The motion is repetitive over equal time interval. The correct answer is option C. The next question. The maximum displacement of a vibrating body from a fixed point is called A. Amplitude, B. Period, C. Frequency, D. Cycle. The correct answer is option A. Amplitude. Thank you for your time. I'm sure you now know what simple harmonic motion is. Till we meet again in the part 2 of this lesson. Bye-bye.